So there are some other forms of lithography. One is X-ray lithography and atomic force microscope. It is a very important instrument. Atomic force microscope, nanolithography. Actually, the deep pan lithography, deep pan nanolithography is similar to the atomic force microscopic nanolithography. And another one is nano imprint lithography. So in the X-ray lithography, you use, we generally use X-ray having wavelength of 0.04 nanometer to 0.5 nanometer of X-rays is used. It is like electron beam lithography. Instead of electron beam, X-ray is used. So it is called X-ray lithography. So these are some characteristics of X-ray lithography, and we do not study more about these types of lithography. I want to just show you two videos on atomic force microscopy and nano imprint lithography. I want to show you those two videos actually, and then we shall go to the another thing, another chapter, or another section rather. First, see what is AFM. X-ray.
An AFM is an atomic force microscope. It lets you see things that are very, very small, all the way down to the nanoscale. How does an AFM work? An AFM uses a very sharp tip to scan over a sample surface.
স্যার ভিডিও দেখা যাচ্ছে না স্যার, ওই যে ফোল্ডারটাই দেখায় বসে আছে।
আজকে কি ডিস্টার্ব করছে কেন বুঝতে পারছি না
স্যার। এটা নতুন সিস্টেম হয়েছে স্যার জুমের।
কি হয়েছে এটা?
স্যার যে অ্যাপ দেখাতে চাবেন স্যার ওইটাই দেখাতে হবে, না হলে দেখাবে না আর কি।
যে অ্যাপ দেখাতে চাবো মানে?
হ্যাঁ ওইটাই স্যার শেয়ার দিতে হবে। এখন স্যার ভিডিও প্লেয়ার দেখাচ্ছেন না, ওই জন্য ওইটা আবার শেয়ার স্ক্রিনে গিয়ে ওইটা দিতে হবে আবার।
ও আচ্ছা, আবার দিলাম, এখানে দিলাম।
An AFM is an atomic force microscope. It lets you see things that are...
না স্যার, ওই যে ভিডিও প্লেয়ারটাই দিতে হবে স্যার।
বুঝি নাই, ভিডিও প্লেয়ারটা দিতে হবে মানে?
শেয়ার স্ক্রিনে স্যার ওই ভিডিও দিতে হবে স্যার কি স্যার?
তাই তো দিচ্ছিলাম। ও আচ্ছা, আগে ভিডিওটা বের করে নিতে হবে,
অন করে স্যার, তারপর ওইটা দিতে হবে।
ও আচ্ছা আচ্ছা, তাহলে আমাকে এইতে চলে যেতে হবে। Again.
An AFM is an atomic force...
এটা কারেক্টার শয়তানি। এটা গেল কোথায়? এবার দেখা যাবে মনে হয়, কিন্তু কথা হচ্ছে এটা গেল কই? আবার এটা চলে আসছে। এটা তো মহা মুশকিলের মামলায় পড়লাম আমি।
An AFM is an
এখন দেখতে পাচ্ছ?
হ্যাঁ স্যার।
এবার দাঁড়া, অন করে নেই এখনো।
An AFM is an atomic force microscope. It lets you see things that are very, very small, all the way down to the nanoscale. How does an AFM work? An AFM uses a cantilever with a very sharp tip to scan over a sample surface. As the tip approaches the surface, the close-range attractive forces between the surface and the tip cause the cantilever to bend towards the surface. However, as the cantilever is brought even closer to the surface, increasingly repulsive forces cause the cantilever to bend away from the surface. An AFM has a Z scanner that moves the cantilever up and down, an XY scanner that moves the sample back and forth underneath the cantilever, and a position detector that records the bending of the cantilever. The position sensor works by tracking a laser beam that is reflected off the flat top of the cantilever. Any bending in the cantilever will cause changes in the direction of the reflected beam. The position detector then tracks and records those beam changes. Using the detection method explained earlier, an AFM images the topography of a sample surface by scanning the cantilever over a region of interest. The raised and lowered features on the sample surface influence the bending of the cantilever measured by the position detector. AFM generates an accurate topographic map of the surface by using a feedback loop to control the height of the tip above the surface. There are two major methods of AFM imaging: contact AFM and non-contact AFM. In contact AFM, the cantilever scans across a sample with its tip touching the sample surface. Because the tip is in contact with the surface, strong repulsive forces cause the cantilever to bend as it passes over the surface features. The advantage of this method is the relative simplicity of its technology. However, there are disadvantages. One disadvantage is that the sample can be damaged by the gouging action of the sharp tip. Another disadvantage is that while the tip is gouging away at the surface, it also grinds down the tip, which reduces the quality of your image. In non-contact AFM, the cantilever oscillates just above the surface while it scans, but the tip does not touch the surface. A precise, high-speed feedback loop is used to keep the cantilever tip from crashing into the surface, thus retaining tip sharpness and leaving the surface untouched. As the tip approaches the surface, interactions between the tip and the surface cause the oscillation amplitude of the cantilever to decrease. The feedback loop corrects for these amplitude deviations and constructs an image of the surface topography. Non-contact AFM has many advantages over contact AFM. It preserves your sample surface because the tip and surface are not touching. By prolonging the sharpness and lifetime of the tip, it allows for high-quality imaging over many scans. This also brings down the total operating cost of the instrument, as tips are expensive to replace. Atomic Force Microscope, or AFM, is a powerful tool that enables you to see, explore, and obtain measurement data from your samples at the nanoscale. For more information, please visit parkafm.com.
ওকে, এটা তোমরা দেখলে যে একটা এএফএম কিভাবে কাজ করে। হ্যাঁ, এটা জাস্ট এরকম যে এখানে দেখো হাতে উঁচু নিচু আছে। আমি যদি এটা দেই, আমার আঙ্গুলটা যদি মুভ করাই, যখন নিচু হবে এটা নিচু হয়ে যাবে, যখন উঁচু হবে আমার আঙ্গুলটা উঁচু হয়ে যাবে। জাস্ট টু সি দ্য সারফেস টপোগ্রাফি, হ্যাঁ, ওই সারফেস টপোগ্রাফিটা দেখার জন্য এটা অ্যাটমিক ফোর্স মাইক্রোস্কোপ। ওটা দেখো টিপটা হচ্ছে ভেরি স্মল টিপ, ওই টিপটা দিয়ে সারফেস টপোগ্রাফিটা দেখে। নাও সারফেস টপোগ্রাফি দেখে আমার তো কোনো লাভ নাই, আমার ব্যাপারটা হচ্ছে ওই রিকোয়ার লিথোগ্রাফি। লিথোগ্রাফি কিভাবে একটা জিনিস আমি একটা জিনিস ড্র করব বা একটা কিছু করব, তো সেখানে করা হয় কি, ওই যে টিপটা দেখেছো, ওই টিপের মাথায় যে জিনিসটা দিয়ে আমি ড্র করব, সে ফর এক্সাম্পল আমি এটা সিলিকন, এই সিলিকনের এই জায়গায় আমি বোরন boron implant করব। We want to implant boron on a silicon substrate. So we will deliver boron with that tip to the silicon substrate in the perfect position, because the tip is very narrow. Because the tip is very narrow, এটা খুব narrow, এটা খুব সূক্ষ্ম। So we can place a boron atom exactly where we want to. Here we want to place a boron. I will place a boron atom here. I will place a boron atom here. I will place a boron atom here. So by that AFM tip, we can do the lithography, just like writing. If I want to write A, then we can write it by a pen. What is a pen? There is a tip on that pen. You see, there is a tip on that pen, and there are some inks. So this tip is of AFM tip, and the inks are boron or phosphorus or whatever you want to impregnate or want to keep it here. So it is called dip pen technique by the AFM microscope. This is the simple way of explaining this, but the actual situation is more complex. Now, the second thing is nano imprint. Oh, I have to do it again. It's nano imprint. Where it is?
পোটেনশিয়ালের সাথে স্যার ডিস্ট্যান্সের যে কার্ভটা দেখায় ওটা কি মিন করে স্যার?
ওটা that is the surface topography. যেটা কার্ভটা দেখাচ্ছে, this is the surface topography. Surface is like that. Surface is like the AFM tip is here. It tips goes lower. Here tips comes higher, and your surface is also lower and higher. So nano imprint. This is the nano imprint lithography. এটা কোনো সাউন্ড নাই, কাজে চিন্তা করো না। এটা জাস্ট দেখো হোয়াট ইজ ন্যানো imprint. Nano imprint lithography, actually it is like a stump. It is like a stump. You prepare a stump and place on a resist, and you will get the your desired what you call the shape, your desired shape. Just place the stump on the resist and do some UV light and give some you treat the UV light. Here it is, you see the stumps are pressed into a polymeric material which is called resist that was previously deposited on the substrate. কোনো সমস্যা হচ্ছে?
স্যার স্ক্রিন তো দেখা যাচ্ছে না।
এইটা নিয়ে তো আরেকটা মুশকিলে পড়ে গেলাম আমি, দেখি। এখন দেখা যাচ্ছে?
জি স্যার, দেখা যাচ্ছে।
Nano imprint lithography is the stumps are pressed into a polymeric material that is previously deposited on the substrate. When the stump is filled with polymer, it is treated by UV light through the stump, obtaining the stump shape. A residual layer of resist is left and can be removed. This is the simple way of explaining nano imprint lithography. I am giving you the simple way because I don't want to go deeper on that nano imprint or X-ray or deep pen lithography. Just these are simple explanation of nano imprint lithography or other types of lithographies. So this is the end of this section. Now we shall go to the next section, not next chapter, next section, which is known as nanomagnetism. Nanomagnetism. So I should open it first, I think. Then share screen. এখন দেখা যাচ্ছে?
Yes, sir.
এটা আসলে সিস্টেমটার সাথে আমি ইয়ে হতে একটু সময় লাগবে আর কি। ওকে, nanomagnetism. We know the magnetic material. We know about the magnetic material. We know the magnetism that are bulk material, that are magnetism of bulk material. What will be the difference with the bulk material and with nanomaterial? If the size of the material is in nano range, will it be like bulk material or will it change? That means, will there be any quantum effect? We'll see it now in nanomagnetism. So magnetic nanoparticles. What are the magnetic nanoparticles? The nanoparticles, the magnetic behavior of nanoparticles, they are known as magnetic nanoparticles. That means some nanoparticles are diamagnetic, some nanoparticles are paramagnetic, some nanoparticles are ferromagnetic. So the magnetic behavior that is shown by your nanoparticles is known as magnetic nanoparticles. Magnetic nanoparticles are types of nanoparticles that can be easily tracked, manipulated, and targeted by external magnetic field. The magnetic nanoparticles are very small nanoparticles, and due to their magnetic nature, they can be tracked. Tracked means where it is, where it can go, that can be tracked by a large magnet or external magnetic field. These magnetic nanoparticles have been focus of research these days. Focus of research these days, that means it is not very old research. It is a research of, say, for example, 10 to 12 years back. 10 to 12 years back, the research on magnetic nanoparticles, say, for example, hardly magnetic research on magnetic nanoparticles starts on 2005 or something. It is a very young field of research, and this is due to its properties, which could increase the potential use of nanomaterial-based catalysts, data storage, and optical fibers. There are the main field of research of magnetic nanoparticle, or the main use of magnetic nanoparticle, is in your biomaterials. We'll see it later. Elements like iron, cobalt, nickel, and their oxides can form magnetic nanoparticles. Say, for example, iron oxide, cobalt oxide, nickel oxide, or iron itself, cobalt itself, they are magnetic nanoparticles. The iron oxide nanoparticles are most common most common. They are used in high electrical stability, chemical stability, mechanical hardness. For that, iron has high electrical stability, chemical stability, mechanical hardness. So iron is used most. The properties and synthetic method of iron nanoparticles, so we'll show it. We'll see it now. So this is a iron nanoparticle. It is a natural nanoparticle, and it is found in our body. So you see, this is a iron nanoatom, iron nanomaterial. This is iron nanomaterial, and it is covered with the cell membranes. In our body, a man on an average has 3 to 4 grams of iron, and 30 milligram per day are exchanged in plasma. So we have iron as ferritin. This iron is a very good magnetic nanoparticle. Now we'll see it now about the magnetic nanoparticle. Now the magnetic properties, if we can recall, we have magnetic properties. We have diamagnetic substances, we have diamagnetic materials, we have paramagnetic materials, we have ferromagnetic materials, we have antiferromagnetic materials, and ferromagnetic materials. There are 5 types of magnetic materials we can see, or 5 types of properties of a material, of some material we can see in the bulk material. Among them, the ferromagnetic material is the most important one, because diamagnetic materials do not show any magnetism, so it is not required by anybody. Paramagnetic materials shows a very small magnetism, shows a very small amount of magnetism under the influence of applied magnetic field. And if you remove the applied magnetic field, paramagnetic material will not show any type of magnetism. Only ferromagnetic material shows magnetism after you remove the applied magnetic field. Wherever you see any magnet, it is made of ferromagnetic material. The antiferromagnetic material, also magnetic moment is 0, and some ferrimagnetic materials is used as magnetic materials, but it is not very much used, because in ferrimagnetic material, the magnetic moment or amount of magnetization is very small. So the ferromagnetic material is very much important. For bulk material as well as the nanomaterial also. So what are the ferromagnetic material? If we can recall, the ferromagnetic material is the material which have spins aligned, which have spins, or which have a large quantity of spin aligned in a single way. The spins are in a single way, and we have domains in the ferromagnetic materials. We have seen the domains in the ferromagnetic materials. One domain, there is second domain, there is third domain, there are 4 domains in a ferromagnetic materials. And there are some domain walls also in a ferromagnetic materials. We always see multi-domains in a ferromagnetic material. And when you magnetize a ferromagnetic material, the domain wall mixes with each other as the amount of magnetization increases, and ultimately we shall get a single wall domain with the magnetic moment, with the magnetization aligned with the applied magnetic field. We have seen it details, and we have a what is called a hysteresis loop for that ferromagnetic material, where there are remanences and coercivities in the hysteresis loop. This hysteresis loop and other domains we have studied details in the magnetic materials. So when we studied magnetic materials, we have studied details. Now, what happens when when the diameter of a ferromagnetic materials reaches to the nanoscale? What happens? When it reaches to the nanoscale, a new type of phenomena occurs, which is called superparamagnetism. A new type of phenomena occurs, which is called superparamagnetism. Now, what is superparamagnetism? Remember it. We are discussing about ferromagnetic materials only, not diamagnetic material, not paramagnetic material, not antiferro or ferri. We are discussing the nano particle of ferromagnetic material. What is superparamagnetism? Superparamagnetism is a form of magnetism which appears in small ferromagnetic or ferrimagnetic nanoparticles. The superparamagnetism property appears, or the superparamagnetism property is shown by only small ferromagnetic or ferrimagnetic nanoparticles. Small means nanoscale. That much is small. Nanoscale is small. So first thing, superparamagnetism is only for ferromagnetic nanoparticles. This property is only for ferromagnetic nanoparticles. Now, insufficiently small nanoparticles, say for example, the size of the particle will be 10 to 20 nanometer, that must sufficiently a small nanoparticle. Magnetization can randomly flip direction under influence of temperature. Magnetization can randomly flip direction. What is magnetization can randomly flip direction? Say for example, this is this red arrow is one direction, and say this also this type of magnetization, all of this in the same direction. You see, the magnetization are all of same direction. In ferromagnetic material, we see that the north-south poles or magnetic poles are all in the same direction, or in a domain, all the atoms have magnetization have in the same direction. Now, what happens? if sufficiently small nanoparticles, magnetization can randomly flip direction. Now, if the material is very much small, then this direction of magnetization flips. Flips means it this is flipping. This is flipping. It goes in this way. It goes in this way. This is flipping. This is flipping. You see, flips from this side to this side. This is called flipping. From this side to this side, from upside to downside, from this side to this side. It is called flipping. Flipping. The direction is flipping. The direction of magnetization is flipping. So it happens when the size of material, ferromagnetic material, is very small. Why it happens? Under the influence of temperature. At room temperature, it flips. Now, in ferromagnetic material, you see, if you can recall, in ferromagnetic material, there is a temperature called Curie temperature, above which temperature the ferromagnetic materials shows paramagnetic behavior. Can you remember a temperature called Curie temperature? Above that Curie temperature, the ferromagnetic material shows the paramagnetic behavior. Say, for example, a ferromagnetic material that have a Curie temperature 60 degrees centigrade. Say, for example, 60 degrees centigrade. That means above 60 degrees centigrade, the ferromagnetic material will not show ferromagnetic property, that will show paramagnetic property. Now, what is paramagnetic property? Paramagnetic property is that the arrows, these arrows are randomly oriented. In a paramagnetic substance, or in diamagnetic substance also, the arrows are randomly oriented. If you apply magnetic field, then in paramagnetic substance, the arrows will align with the applied magnetic field, and in diamagnetic substance, the arrows will align opposite to the applied magnetic field. But in a paramagnetic substance, these arrows are randomly oriented. These arrows are randomly oriented. So, a ferromagnetic substance, if we consider a bulk ferromagnetic substance, in a bulk ferromagnetic substance, the arrows are aligned in the same way. But at 60 degrees centigrade, what happened? The arrows will be randomly oriented. Why? Why? Because of temperature. This temperature causes destroys the alignment, and the arrows will the magnetization becomes randomly oriented. Here also, in case of ferromagnetic nanomaterials, you will see at room temperature, that will be randomly oriented. That means what happens? They flip the direction. Say this is in this direction, this will be in this direction, and after some time this will be again in the opposite direction, this will be in upward direction, this will be again in downward direction, this will be upward direction, this will be upward direction, and again another one will be downward direction. This is called flipping your magnetization. The typical time between two flips is called nil relaxation time. Say, for example, this is now in this way. Now, after some time, this arrow will flip to the opposite direction, and this arrow will flip to the upward direction. And this time gap is known as nil relaxation time. Say, for example, this is now in this way, and after 1 second, this will be in the downward direction, and this will be in the upward direction. Then this 1 second is known as nil relaxation time. The typical time between two flips is called nil relaxation time. Now, in the absence of an external magnetic field, when the time used to measure the magnetization of nanoparticle is much longer than nil relaxation time, their magnetization appears to be in zero. So you see, in absence of any magnetic field, will you get any magnetization? Say, for example, there are 4 arrows. If I draw one more arrow, if I draw one more arrow, if I draw one more arrow, what will be the net magnetization of this domain? What will be the net magnetization of this domain? It will be zero. Zero. Why it will be zero? Because 2 is downwards and 2 is upwards. Now, when it will happen? It will happen if if the measurement time is greater than 1 second. That means the time required to measure the magnetization of this system will be greater than 1 second. Say, for example, if you draw this by this way, it will be more better. This is one stage, say, for example, and this is another stage of flipping. This is another stage of flipping. This is one stage of flipping, and this is another stage of flipping. So let us suppose this is a domain, and this is another domain, or same domain. Say this is a domain, and after 1 second, these 3 arrows will flip to these 3 upward arrows. These 3 downward arrows will flip to these 3 downward arrows, will flip to these 3 upward arrows. To flip these 3 downward arrows to upward arrows, the time required is 1 second. And this is called your nil relaxation time. Now let us suppose you want to measure the magnetization, the amount of magnetization of this system. And to measure this magnetization, you require 5 seconds to do the different things. To measure this magnetization, you require 5 seconds. Within these 5 seconds, these arrows, this magnetization will flip 5 times to downwards to upwards, downwards to upwards, downwards to upwards. Sometimes it will be downwards and sometimes it will be upwards. Sometimes it will be downwards and sometimes it will be upwards. So you will not get any magnetization, any total magnetization, because sometimes it is upwards and sometimes it is downwards. Sometimes it is upwards and sometimes it is downwards. So you will not get any magnetization. But if you have the measurement time, say for example, half second, it is below 1 second, then you will get only downward or only upward, because to flip from downward to upward, you require 1 second, but you can measure the magnetization within a half second. So you will get a net magnetization either for downward or for upward, because there is no time, no flipping will occur within half second. So the measurement of magnetization will depend on the measurement time. If the measurement time is greater than flipping time, then you will get magnetic moment 0. Now, if the measurement time is less than the flipping time, then you will get certain magnetization or certain magnetic moment. That is known as that is the dependence on the nil relaxation time. Now, if the measurement time is greater than nil relaxation time, then you will get the total magnetization 0, and this property is known as superparamagnetism, or you can call the material is in superparamagnetic state. You will get 0. You will get the magnetization 0. So in absence of magnetic field, you see it is in absence of magnetic field. So what is superparamagnetic? In absence of magnetic field, if in absence of magnetic field, if a ferromagnetic nanoparticle, if you measure the magnetization of a ferromagnetic nanoparticle, or if you want to measure the magnetic moment of a ferromagnetic nanoparticle, you will get the net magnetization value 0 if your if your measurement time is greater than nil relaxation time. This phenomena is known as supermagnetism phenomena. But if the measurement time is less than your nil relaxation time, you will get a definite magnetization or definite magnetic moment. That will not be superparamagnetism. You will get a definite magnetic moment like a ferromagnetic substance. So in the absence of an external magnetic field, when the time used to measure the magnetization of nanoparticle is much longer than nil relaxation time, their magnetization appears to be an average 0. You will get 0. Why you will get 0? Because they will flip from this side to this side, this side to this side. Sometimes you will get +5 and sometimes you will get -5. +5, -5, +5, -5, and ultimately you will get 0. So they are said to be in the superparamagnetic state. In this state, an external magnetic field is able to magnetize the nanoparticles similarly to a paramagnet. So superparamagnetic means it is paramagnetic. Okay, now it shows the paramagnetic behavior. You will get the magnetism 0 as the paramagnetic. Now, if you place a magnetic field, then it will align to the magnetic field, and you will get a definite magnetic moment like paramagnetic substance. But the magnetic moment is much larger than the paramagnetic substance. That's why it is called super. It is not like the magnetic field is not like paramagnetic substance. Say, for example, in a normal paramagnetic substance, the magnetic field, if you place a external magnetic field, then you will find the magnetic moment of normal paramagnetic substance, say, for example, 5. But if it is a ferromagnetic nanomaterial, and if you apply magnetic field on it, you will get magnetic moment of that ferromagnetic material, and it will be like 50. So there is a difference of ferromagnetic and paramagnetic substance. In paramagnetic substance, you will get a small magnetic moment. But in ferromagnetic substance, you will get a large magnetic moment when you apply magnetic field. But if you don't apply magnetic field, in case of paramagnetic substance, you will get magnetic moment 0. And in case of ferromagnetic substance also, you will get magnetic moment 0 if the measurement time is greater than nil realization time. That's why it is called paramagnetism. And why super? Because the magnetic moment is much larger than paramagnetic substance. That is called superparamagnetic. In this way, an external magnetic field is able to magnetize the nanoparticles similarly to a paramagnet. However, their magnetic susceptibility is much larger than the paramagnet. Their magnetic susceptibility is much larger than paramagnet. The magnetic susceptibility of paramagnetic is say 5, but for a paramagnetic substance, it will be 50. That is called superparamagnetic phenomena or superparamagnetism. In absence of magnetic field, the particle behave like a paramagnetic material, but with the presence of magnetic field, the particle behave like a ferromagnetic material. So, superparamagnetism do not depend on Curie temperature, but depends on the blocking temperature. What is blocking temperature? Blocking temperature or blocking temperature means flipping temperature. That temperature that can flip, that will flip. And you known as the blocking time or the nil relaxation time. Actually, the superparamagnetism property depends on the actually nil relaxation time. So again, we'll see without external magnetic field, the net moment is 0. As soon as the external field applied, the nanoparticle reacts similar to paramagnet, with one exception that the magnetic susceptibility is much larger. So S, because it reacts like paramagnet, so it is called paramagnet. And S, because their magnetic susceptibility is larger, that is called super paramagnet. আমাকে বলো, কোনো কোশ্চেন আছে? বুঝেছো নাকি বুঝো নাই? কোনো কোশ্চেন থাকলে বলো। Is there any question? বলো আমাকে। What is super paramagnetism? গোটা ন্যানোম্যাগনেটিজমের এটাই হচ্ছে একমাত্র জিনিস, সুপার প্যারাম্যাগনেটিজম, নাথিং এলস। তুমি দেখো, যদি 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 বাল্ক ম্যাটেরিয়াল দেখো, বাল্ক ম্যাটেরিয়ালের মধ্যে হোয়াট ইজ দ্য মেইন থিং? ইট ইজ ফেরোম্যাগনেটিজম। হ্যাঁ, other substances are not so much important. Diamagnetic substance, paramagnetic substance, they are not so much important. Ferromagnetic substance is very much important because all magnets are ferro. Now, this ferromagnetic substances shows super paramagnetic behavior. This ferromagnetic substances show super paramagnetic behavior when the size reduced to nano. This is the only thing in nanomagnetism. Now, আমাকে যদি তোমরা কেউ যদি না বুঝে থাকো আমাকে জিজ্ঞাসা করো।
স্যার, টু ফ্লিপস বলছে দ্যাট দ্য টিপিক্যাল টাইম বিটুইন টু ফ্লিপস, তাহলে টু ফ্লিপস মানে কি একবার গিয়ে আবার আগের
না
জায়গায়?
no, টু ফ্লিপস মিন্স একটা ফ্লিপ আর একটা ফ্লিপ, একটা এরকম করছে, সব সময় এরকম করছে, এই জন্য এটাকে টু বলছে। অলওয়েজ ফ্লিপিং লাইক দিস এন্ড দিস, 0 ডিগ্রি 180 ডিগ্রি, 0 ডিগ্রি 180 ডিগ্রি, টু ফ্লিপস, এই জন্য এটাকে টু ফ্লিপস বলছে।
আর স্যার বাল্ক ম্যাটেরিয়ালে তো অটোমেটিক ফ্লিপ গুলো হয় না, ন্যানো
না
ম্যাটেরিয়াল
হয় at 300 degrees. Say for example, Curie temperature is 60 degrees centigrade. তো যখন 60 ডিগ্রি সেন্টিগ্রেড আসবে তখন বাল্ক ম্যাটেরিয়াল গুলো ফ্লিপ করতে থাকবে, বাট নট 0 ডিগ্রি 280 ডিগ্রি এরকম না। ইট মে ফ্লিপ ইন দিস ওয়ে অর ইট মে ফ্লিপ ইন দিস ওয়ে, মানে তাদের ওরিয়েন্টেশন ডিফারেন্ট হবে, যার ফলে ইট উইল শো দ্য প্যারাম্যাগনেটিক বিহেভিয়ার। Bulk material হবে, but at a high temperature that is called Curie temperature. Now, what is the nil relaxation time? Our main importance, the nil relaxation times is the time between flipping from 0 degree to 180 degree. To flip from 0 degree to 180 degree, it requires a time. It is around 10 to the power minus 12 seconds or 10 to the power minus 10 seconds. Let us suppose it is 1 second. This 1 second is the nil relaxation time. Now, if you can measure the magnetic moment within 1 second, then you will get either this way or you will get either this way. But if you take, say for example, 5 seconds to measure the magnetic susceptibility, then you will find that the materials, in 1 second it is like that, and another second it will be like that, in another second it will be like that, in another second it will be like that. You will not get any certain your magnetic moment, so it will be 0. But if you can measure it below 1 second, you will find this is either in this way or this is either in this way. So you will get a definite magnetic moment. This is not your super paramagnetism. If you can measure the magnetism within half second, that is not super paramagnetism. The super paramagnetism is if you can measure, if you measure this above nil relaxation time, the measurement time is above nil relaxation time, then the behavior is the super paramagnetism. Generally, we cannot measure any magnetic moment within 10 to the power minus 12 seconds. The nil relaxation time actually is about 10 to the power minus 12 seconds. Generally, we cannot measure a magnetic moment within 10 to the power minus 12 seconds. So we always get the super paramagnetism property of a ferromagnetic substance. Bolo. Any question? Any question? Anybody? কারণ এই জিনিসটা যদি না বুঝো এরপরের জিনিস কিছুই বুঝবে না। And this type of এই যে সুপার প্যারাম্যাগনেটিজম, এই ডেফিনেশনটা 2010 এর আগে মোটামুটি জানতোই না কেউ। হ্যাঁ, it is very new invention, rather new explanation. এখানে অনেকগুলো ম্যাথমেটিক্স আছে, but this is the main thing. Now this is the super paramagnetism. Now if you apply magnetic field, it is without applying magnetic field. Now what happened if you apply magnetic field? It will behave like paramagnetic substance. It will behave like some, then it will not flip from this way to this way, this way to this way. It will align to the applied field. Now you will get a magnetic moment of this ferromagnetic substance, which is much higher than any paramagnetic material. That's it. That's why it is called super paramagnetism. Super is because its magnetic moment is much higher than paramagnetic substance. ঠিক আছে, বুঝা গেছে? আর কারো বুঝা গেছে? সবাই বুঝেছো? Any problem? আমজাদ, বুঝেছো?
জি স্যার, বুঝতে পারছি।
বুঝতে পেরেছো সুপার প্যারাম্যাগনেটিজম? ভেরি গুড, ভেরি গুড। নাও আমি তো আবার আমাকে ওইটা খুলতে হবে, আবার এই সমস্ত করতে হবে। দেখা যাচ্ছে না আটকে আছে? দেখা যাচ্ছে না? ভেরি গুড। Now these are the sizes of the particle. We have a nanoparticle. Nanoparticle means, say for example, this is a nanoparticle, and this is a bulk material. If you see the bulk material, of course it is ferromagnetic material. Of course, ferromagnetic material. If you see the bulk material of a ferromagnetic material, you will find that there are domains, and these are the domain walls. There are domains, and for that domains we got the hysteresis and hysteresis loops. All these things you have studied before. These are the domains. Now, if you decrease the size of a ferromagnetic particle, say for example this way, there are also some domains. Now, if you decrease it again, you will get a single domain particle. It is still not a nanoparticle, but you will get a single domain ferromagnetic particle. There is no multi-domain like here. So if you decrease the size of a ferromagnetic particle, you will get single domain particle rather than multi-domain particle. So in a nanomaterial, there will be a single domain particle. There will be no multi-domain, or there will be no domain wall. Why? As because this domain wall is associated with some energy, and if the size reduces, this energy becomes higher. So nanoparticles, or so small size particles, will not require, or will not allow any domain wall inside it, because it will cost more energy, or high amount of energy for them. But they can afford that much of energy to have a domain wall here. So they have domain walls here, but they do not have. Now you see, if you see, this is a ferromagnetic material that has with no applied magnetic field. So in this domain, all these atoms are aligned in one way. In this domain, all are another way. But if you see that nanomaterial, if you see superparamagnetic nanoparticle, you see all the particles will align in the same way, because there will be no domain walls. I told you just earlier that just now that there will be no domain wall because of some energy constants. So there will be no domain wall here. All that materials are in this way. Now, in presence of magnetic field, you will see all the magnetic moments are aligned to the magnetic field here in the multi-domain particle, in ferromagnetic particle, and same for superparamagnetic particle. It is same for superparamagnetic particle. So a ferromagnetic particle of large size, and this is a ferromagnetic particle of a small size. This is the ferromagnetic particle of large size and the small size, and with applied field and without, sorry, this is with applied field and this is without applied field. Now there are some small equations. This is called Neil-Arrhenius equation. This is called Neil-Arrhenius equation for superparamagnetism. Tau is equal to tau 0 exponential E by kVt. Tau is the average time that it takes for a ferromagnetic কি হলো আমি তো বুঝতে পারছি না। কারেন্ট তো ছিল, সবই ছিল। হ্যালো, কেউ কি আসো?
জি স্যার,
তো সবই ছিল, হঠাৎ করে এরকম কেন করছে বুঝতে পারছি না। আরো একবার হয়েছিল এরকম 2-3 মাস আগে, মানে এরকম ইট ইজ ফ্লিপিং।
নেটওয়ার্ক ওয়াইফাই
না, ইট ইজ কল ফ্লিপিং, যাচ্ছে আসছে, যাচ্ছে আসছে, দিস ইজ কল ফ্লিপিং। হ্যাঁ, নিচে উপরে, নিচে উপরে, দিস ইজ কল ফ্লিপিং ইওর। তো আমি যেটা, হ্যাঁ, আমি যেটা করছিলাম, আবার একটু যাই, দেখা যাচ্ছে? দেখা যাচ্ছে?
Yes, sir.
হ্যাঁ।
Yes, sir.
সো টাওটা কি বলছিলাম? টাওটা হচ্ছে নীল রিল্যাক্সেশন টাইম, average length of time that it takes for a ferromagnetic cluster to randomly flip direction as a result of thermal fluctuations. হ্যাঁ, এইটাতে দেখো, this is a ferromagnetic cluster. This is a ferromagnetic cluster. It will randomly flip to this way or in 180 degree. This way or this way, this way to this way, this way to this way. It will randomly flip. And the time required for this flipping is called nil relaxation time, and it is denoted by tau. And a tau naught is a constant-like thing, which is characteristic of material, is the anisotropic energy, which is proportional to the volume of the substance. And what is E? E is equal to kV. kV is the anisotropy energy density constant. These are the normal one equation, and another one is blocking temperature. Blocking temperature means that at that temperature, the temperature on which flipping is done, that is called your blocking temperature. Flipping is done. So if the temperature or time is greater than TB, then tau less than tau naught, then it will behave like paramagnetic substance, which you call which I told you, and it will magnetic ordering open loops. You will get magnetic substance. These are the you see, temperature is when the temperature is below blocking temperature, we'll get a definite magnetic moment. But if temperature is above the blocking temperature, then you will not get any magnetic moment. It will flip. It will flip. So properties of super paramagnetic materials, their particle size will be less than 30 nanometer. It will be single domain structure. It has high value of saturation magnetization, high magnetic susceptibility, high magnetocrystalline anisotropy, and the hysteresis loop magnetization or HMH curve. This is the hysteresis loop. We'll tell it tomorrow. We'll tell it tomorrow. This is the hysteresis loop. We'll explain this tomorrow. This is the hysteresis loop of super paramagnetic substances. আমরা সামনের দিন এটা দেখবো।